Okay, now we will have a short discussion about the power flow formulation, okay? If you are familiar with power system modeling and simulation, you must understand that the general form to represent a power system is using what we call the differential algebraic equations. You must remember that all the dynamic of the power system is represented by a set, can be represented by a set of first order differential equations. That is the equation here, F. And also all the algebraic nonlinear relationships inside the power system can be represented using a set of nonlinear equation G. Okay, the algebraic differential equations, they are the basic of studying the power system dynamic. However, right now we are working only at the steady state condition of the power system. For that reason, we can neglect the set of equations related with the differential equations F, and we just focus on the function G. The function G represents the algebraic equations, nonlinear equation representing the network basically. And for the power flow analysis, what is important is that G represents the power balance equation at the system, okay? If you remember, we can write the power balance equation in a very simple way. All the generated power must be equal to the consumption plus the losses. If you look the equation here that I put below, over there what you can see is the set of two n equations that represent the active power and the reactive power balance, okay? Coming back to my general explanation, G represent the set of nonlinear equations. Those nonlinear equations are based on the power balance equations. However, we must understand that X and Y, they represent set of variables inside the power system, and we can classify for the power flow analysis the variables in three main groups. The uncontrolled variables, for instance, the active and reactive power, because that is a consumption and that is coming from the desires of the customers. But then we have independent and controlled variables. In that case, could be the generation provided by those synchronous generators connected to the grid. And then we have some dependent variables. For instance, if we are working in a transmission system, the bus bar, the voltage and angle will depend on the power flow that is moving on the transmission line. What I'm trying to say is the power flow problem is basically a nonlinear problem, that they are a set of variables, and depending on the known and unknown variables, we can have uncontrolled variables, dependent variables, and independent variables, okay? But coming back to my explanation, the core of the load flow, the core of the power flow is the power balance equations. However, we demonstrate that those equations are nonlinear. And any power system analysis software, what they are doing is they are formulating the set of power balance equations based on the data that you provide to the software. And in this case, the nonlinear equations, they don't have analytical solution. They don't have a closed form solution. Even for the lossless case, in solving those equations by hand could be time consuming, okay? What we need to do is, usually we use numerical techniques, numerical iterative techniques, in order to solve the nonlinear set of equations representing the power flow problem. The power balance problem require the solution of those simultaneous nonlinear power balance equations. solution, okay? There are many techniques. If you are familiar with numerical methods, they are very large number of methods: bisection, regular falsi, modified regular falsi. They are a family of Newton methods. They are a family of seconds method. They are newest method like the steepest descents and so on. However, from the academic point of view, basically there are three basic algorithms that we use for solving the power flow. One of them, the most basic, Jacobi. The second one is Gauss-Seidel, and probably the top of them is the Newton-Raphson, okay? Each numerical method has advantages and disadvantages. However, I will discuss that in the next section, okay? Basically, when we are talking about solving the power balance equations, there are basically three methods: the Jacobi method, the Gauss-Seidel method, and the Newton-Raphson method. To be honest, the Jacobi method is the most simple and easy to implement from the mathematical point of view. However, it's one of the, let's say, slowest method in order to get convergency and to get a good solution. Gauss-Seidel, typically they have a better convergency compared with Gauss-Seidel, but is poor convergency when you compare with any of the Newton family methods, okay? For that reason, it's not quite use Jacobi or Gauss-Seidel for serious power system analysis software. If you look all the power system analysis software, almost all of them, they are using one of the methods coming from the Newton family. The most used is the Newton-Raphson, okay? Newton family methods, they are very well known because they have the ability to converge quite fast for starting from very poor initial conditions. However, one difference between power system problem and any other mathematical problem is that the initial conditions that you use to solve the equations, they are close to the solution in any way, because we use what we've called the flat start for the numerical solution. A flat start means nominal condition for voltages 1 per unit, and in normal conditions, even in a very poor power system, the voltage are nearby to 1 per unit. For that reason, Newton-Raphson is a very good method for solving the power flow. Also, because some other structural characteristic of the power system that I will not discuss regarding the admittance matrix, to be honest, Newton methods is quite robust for the solution, okay? Now what I will do is I will have a short discussion because I would like that my students be familiar with the network representation and calculation, okay? Something that any student must realize is that typically in any bus bar inside your power system, we can identify 4 variables to define the power flow, okay? If you look at single bus bar, there are 4 variables: the voltage magnitude, the voltage angle, the active power, and the reactive power, okay? You can classify any bus bar for a steady-state analysis of positive sequence load flow, power flow. You can use 4 variables to describe the performance. However, what is the good news and the bad news? Well, there are some bus bars that you know P and Q, there are some bus bars that you know V and delta, and there are some bus bars that you know V and P. And that is the classical classification of bus bar for power flow analysis. Typically, we use 3 different types of bus bar inside the power flow analysis. One bus bar that we call reference or slack bus bar. At the slack or bus bar reference bar, we know the voltage and magnitude, but it's unknown P and Q. Okay, and what I'm trying to say is the slack bus bar is typically one of the bus bar inside the power system, and we assume that the voltage is fully defined magnitude and angle. However, if you define those two quantities, you have two quantities, P and Q, active and reactive power, that they are unknown. Okay? On the other side, we have the load bus bar, and we use the name PQ bus bar. PQ bus bar because the known variables are P and Q, active and reactive power respectively. However, in those bus bars, the unknown variable is voltage and voltage magnitude and angle defining the position of that voltage. Okay? In the middle, we have a very interesting definition, and that is the generation bus bar. Typically, we use the name PV bus bar. The PV bus bar is a bus bar where the active power P is known, is defined, and also the voltage that is used is defined or known. Okay? One of the things about the PV bus bar is that the reactive power in this case is used to keep constant this voltage. Okay, I will discuss more about voltage regulation and the effects of those limits on the generators in the practical case. Okay, but coming back to the slack bus bar, as you define two parameters, magnitude and angle for the voltage, the unknown variables are coming in the way of active and reactive power, and these have an extremely important effect when you are calculating the steady state condition or the power flow of your power system, because you must realize that the slack bus bar is the bus bar coping with all the losses inside your power system. If you remember, the balance equations say all generation is equal to all consumption plus the losses. If you have PQ bus bars, in all of them you know P and Q. And if you have some generations PV bus bars, you know P. That means that the only bus bar that the active power P is unknown is the slack bus bar. As a consequence, all the active power losses and reactive power losses will be covered by the slack bus bar. That is the reason that some people call this the bus bar for compensation. Okay. However, if you want to know more about this discussion, you can go to my YouTube channel and have watch my video about full explanation of power flow. Okay. Okay. In this section, I will present a very interesting feature that you can find in DIgSILENT PowerFactory. It has been many years with this feature inside PowerFactory, but I am creating this video and including this example because many people they don't use this functionality, and sometimes it's quite practical. Okay. There are many cases during the planning studies that you are interested to know what is the difference between two different scenarios in terms of the steady-state performance. For instance, if one load is increased or one load is switched off, what are the changes that you can find inside the power system? Or what is the impact on the active power losses if you increase a load? I mean, there are many situations inside the power system planning that you are interested to know changes, and in those cases, it's very useful if you have a tool that allows you to make comparison between cases. DIgSILENT PowerFactory is one of the well-known, and I will say probably one of the best power system analysis. There is a functionality for power flow analysis inside PowerFactory, but also PowerFactory include what I call comparison between cases, and that is a functionality included by default in PowerFactory. Okay. The functionality is extremely simple. What you need to do is basically follow 4 steps, okay? Follow 4 steps. Those 4 steps will allow you to automatically run the comparison between 2 scenarios, and you can customize the style or the way that you are calculating the difference between those scenarios, okay? For this example, I will be using the system, the PM Anderson system. You are familiar with the PM Anderson system, 9 bus bars and 3 loads, and there is a big transmission network over there in 230 kV, okay? The step number 1 in general case is what you need to do is run a load flow, okay? All my students, all my followers, you must know how to calculate a load flow. That is the ComLdf. There is a specific button on the top of the tool bus bar, and you can press that and select execute, and you get the result, numerical result here in the text box, okay? And this is because this is an static calculation, okay? Next step. There is a button in the bus bar, you can see here, and that is the icon, and the icon in order to store the base case result, okay? This button is basically, when you press this button, this icon, what you are doing is storing in memory all the numerical results coming inside your power flow analysis, okay? PowerFactory will give you back a window that say, okay, I just store in memory all your numerical results coming from the load flow that you already did, and I will use the name case A for these results, okay? Then the next step is, okay, now you are able to make the changes inside the network that you want to do. For instance, you can close and open switches, that means generator, loads, and so on. You can change the settings of a load, for instance. You can change parameters of any device, or even changing calculation cases, adding or deleting components, okay? In this case, what I will do is something very simple. To illustrate the case, I will say, okay, let me switch off the load A that is located at bus bar number 5. You can click on the circuit breaker, it will open, you can see the gray color because now this device is out of service, is not connected to the grid, okay? What is the step number 4? Well, the step number 4 is run again your load flow. You are familiar with the ComLdf. Press the button, execute, and PowerFactory will come back to you and say, okay, now we have numerical results. We store those numerical results in memory. The name of this case is the case B, okay? Now, what we want to do is represent or present some comparison, okay? In order to present the comparisons, what we need to do is going again to the toolbar, and there is a button that allows you to calculate the difference between the two cases, okay? When you press that button, another window will appear, and that is for the command DIFF. The command DIFF is the command that will allow you to calculate the difference between the two different cases. And in this window, you can configure what is the way that you want to calculate this difference, okay? For this specific case, I will select case B minus case A. And all my students must remember case A was the base case, and the case B is when you remove the load A, okay? Now, let's see the numerical results. I was explaining case A, load A is working. We can see here 125 megawatts. That is the active power on load A. And here we have a voltage of 1 per unit minus 4 degrees, okay? Then when we run the case B show me that we have the load is open, that means 0 megawatts going to load A. But there are many changes. One of them, you can see here, the voltage now is 1.05 per unit, and the angle is 1.7. Okay. Also, something really interesting is that you can see in the summary bots, in case A, the active power losses, it was around 4.60 for the losses for active power, and now the active losses 4.91. Okay, now let's do the following. We use the button, we create the comparison, and the comparison that we are running is case B minus case A. Okay, if we come back here, the original case is 125 and the final case is 0. However, you must remember that the difference that we are calculating is case B 0 minus case A 125. That means that the change is minus 125. If you look the results using the commands difference, wow, we can see here the difference. In this case, is showing that the active power is minus 125. But what we are showing here is that the active power drop 125 megawatts. Okay, coming back to the voltage, I would like to show you the voltage. Especially the voltage in this case is moving from 1 per unit to 1.05. That means that the difference is 0.05. That means that the voltage is increasing 0.05 per unit when you are switching off the load A. Okay? Here I present to you a comparison. Now we are comparing using the absolute value. You can see here, this is case B, this is case A, and then the difference. To be honest, you can see that there are changes on the voltage around 11.8 kilovolts in the bus bars 5, and also that is equivalent to 0.05 per unit. The angle, there is a big change because we are moving from minus 4 degrees to 4.7. The absolute change in this case is 8.7 degree. Okay. Below in this slide, you will find using the relative comparison. This is case B minus case A. Divide by case A, considering as a base the case A. That means we are calculating here the relative change where the base case is case A. Now you can see that there are changes. 5.15 is the percentage change on the voltage magnitude. And for the angle, wow, there is a big change. There is a massive change. Minus 287%. Okay? Well, in a minute I will go and do this inside DIgSILENT PowerFactory, and I will show you in real time what is this new feature. I hope you enjoyed this feature and you learn how to use it because it's quite typical and quite practical. Okay? You can use this also for short circuit analysis. Okay? Well, now the plan is to go to PowerFactory and test the functionality, the new functionality that we were discussing about, a comparison between cases. For this very specific case, I will use the PM Anderson 9-bus system that we already prepared. Okay. Let's jump to PowerFactory. Okay, as you can see here, we have the PM Anderson 9-bus system, and initially what we can do is just run a classical load flow. Okay, you must remember to run the classical load flow. What you need to do is go to the toolbar and select the icon for the command load flow. Okay, then as you can see, there is a window that allows the configuration of the load flow study. In this case, what we need to be sure is that all the options are deactivated and the only thing that is active is the calculation method. In this case, we are using the very classical AC load flow. That means that we assume that the network is totally symmetrical and balanced, and as a consequence, we can use the positive sequence model. Okay. When we run the load flow, of course, in this case, they are not results, but we can show using this small icon here, we can show the results using the result layer. Okay. In this case, what I will do is a small zoom here in the area of the load bus of the load A connected to the bus bar number 5. Okay, I think you can see there a power demand over here, 125 megawatts and 50 MVR, and the normal voltage here is 1.0 per unit and -5 degrees. Okay. Well, now what we can do is I would like to show you how to use this very powerful function that is comparing results. Okay, the first step is, okay, we need to switch on the functionality, and PowerFactory say to us, okay, we store all the results, the numerical result of your load flow into variables, and in this case, the set of variable numerical result of the load flow, they are stored in case A. Okay. Then, following the explanation that I did before, the plan is, okay, let's switch off this load. Okay, I will use a very basic action here, double clicking at the circuit breaker, and in this case we are switching off, open the circuit breaker of this load. Okay, now what we can do is let's run again the load flow, the classical AC load flow, and then PowerFactory come back to you and say, okay, now all the numerical results of this load flow case, they are stored in the calculations presented as case B. And also PowerFactory say to you, okay, all the results will be presented or show in the way of deviation compared with a percentage deviation compared with the case A. Okay, however you can see here there is another button on the toolbar, and in this case you can edit and define what kind of comparisons you would like to do. In this case, what you need to remember is case A was the first simulation, case B the second simulation, and for instance, what I will do now is I will compare the case but using just absolute value. I mean, in this case, the result, numerical result from the case B will be subtracted or to the case A, and that will be the results that you will see. Okay, now let me amplify here, and as you can see there is a minus 125 megawatts. In this case, the results are presented in real units, megawatts, because we are creating the difference between two cases, case B minus case A. Case A was the load totally connected and consuming 125, and the case B was the case that we switch off the load. In that case, the load is 0. As a consequence, case B minus case A that we define here in the comparison results, it will be negative 125, okay? Also is something similar is happening with the voltage, okay? What was happening is at the very beginning we have a voltage that was 1.0 per unit and minus 4 degrees, but then when we open the circuit breaker of this load, the voltage increased, and as you can see now we have a voltage, an increased voltage of 0.05 per unit, and this is a voltage increase at the bus bar number 5, okay? Here you can see that was the comparison, but also these changes are located in any result box that you can see, okay? What I'm trying to say, for instance, in this line, the change on power between case B and A is 110 megawatts, okay? That is a very useful tool, okay? I highly suggest that you be familiar with this very interesting configuration here for the comparison between cases, and also if you want to use color results, also that is an option. You can be able to edit and define a specific color as you wish, and depending of the percentage of variation that you want to show, okay? Well, this is all regarding this very specific example, and now let's move to the next case, okay? Well, the next step is the example number 3. Here, what we want to do is use the power flow in order to see how the performance of your power system change when there is some voltage control and voltage dependence, okay? Voltage dependence at the loads, okay? Something that is really interesting here is also I have included a very specific example. In this case, we are using a very small generator connected to one load, and that is what we call distributed generation, okay? In this example, we will be using this small generator in order to demonstrate what is the effect that we can get when we install distributed generation, okay? If you are with me at this moment, you can see the starting point of this is, well, we will be using for this example a very basic and very simple typical distribution system. As you can see, is a radial configuration, okay? You can see bus bar number 1. Bus bar number 1 is connected to an external grid. There is a a distribution line going to the bus bar number 2, then going to bus bar number 3, then going to bus bar number 4, and then going to bus bar number 5. Okay, they are static loads connect bus bar 2, 3, 4, and 5. Okay, this is a typical radial configuration that you can find in many countries. It could be something representative of primary distribution level in some countries. Okay, and here in bus bar number 4, you can recognize that there is a synchronous machine. In this case, we say that this synchronous machine is an equivalent. Is a very small machine, but that is what we call distributed generation. Okay, we call this generator distributed generation because probably 20 or 25 years ago the technology started to evolve. Okay, and that's make that small generators start to produce electricity with prices that can be competitive with the big generators. Okay, that was a very
huge step forward on the generation side of power system. Okay, from there, many technologies has evolved in the market, and the cost has been reduced, especially the PV system, the photovoltaic system. Today, there are many countries around the world that you have a property, for instance, your home, and you can install on the roof of your home a set of PV panels, and from there you can produce electricity and use your electricity. But also in some countries, the market and the regulations and the law allow that if you have more power, that the power that you are consuming, you can export that power to the grid, and that represents some economical benefit that you can get from the PV system that you have at home. Okay, in other countries, DG is mainly a business opportunity. In some countries, it's something that is just a possibility. Okay. Well, but the topic here is not talking about or discussing about distributed generation. The topic here is, okay, let's see how this small generator directly connected to the load, locally connected to the load, can improve or can make changes regarding the voltage profile, I mean the voltage on your system, okay? In this case, okay, we have included the DG over there, but to be honest, the first step that I would like to show you is, okay, this small 5-bus network is a very poor network, okay? First step is we will switch off this generator. The DG generator is disconnected, okay? If we disconnect the DG generator, you will see that at the very beginning of this feeder, let's say this is a distribution feeder, you can see if we disconnect the DG, we can realize that at the very beginning of the feeder, what we call the head of the feeder, the voltage is 1.05 per units. And when you move down to the tail of this distribution feeder, you can see 0.97, 0.91, and then the voltage starts to be quite poor. You can see here 0.86, and at the end, at the tail of this feeder, bus bar number 5, the voltage is so low that is 0.82, okay? To be honest, in this case, you realize that this distribution feeder is totally operating in a steady-state condition, but is outside the quality standards, okay? Everyone must recognize that there are some legislation and some documents that say that the voltage that you receive at home or the voltage that is provided by the company must be inside a band. In some countries, the size of that band, the maximum and minimum voltage that is allowed inside the network in a steady-state condition is defined in percentage. In some countries could be 10%, others could be 8 or 5%, or even less, depending on the location, or even bigger. Okay, in some countries they allow even voltage drops even larger than 10%. Okay. However, in this case, this is a very poor feeder with a very bad load profile. However, the idea here is to use this feeder to identify some measurements and some effects related with voltage control and voltage dependency. Okay? As you must be aware, PowerFactory is a very amazing tool and very complex tool in order to simulate almost every single effect that you can consider in your power flow. Okay, when you open the command load flow, we did a few minutes ago, but we use the basic configuration. The basic configuration is using the classical AC load flow, positive sequence, and for balanced network. Okay. However, there is a small area here at the bottom, and you can see load options. Okay. What I want to spend a few minutes here is talking about this one that say voltage dependence of loads. Okay. Something that is very important in power system is that the power demands is very sensible in some cases to the voltage variation, okay? When the voltage change, increase or decrease, there is a change on the power demands, let's say megawatts, okay? And that voltage dependence has been studied by many electrical engineers for many years, okay? Something that we realize is that there is a very simple way to create the mathematical model to describe the voltage variations and to represent the changes on the active and reactive power when they are voltage variation, okay? If you look over here, there are two very interesting, two very important equations, one related with active power and the other one related with reactive power, okay? You can see this equation is a polynomial equation, and there are 1, 2, and 3 elements here, and U represent the voltage, the real voltage that you have in your system, and U0 represent the voltage, the nominal voltage of your load. Okay, what I'm trying to say is this term, this second term, and this third term, they represent changes, and you can imagine those changes like per unit quantities, basically on the voltage, okay? Now we have some exponents here. You can see A for P, B, P, and CP. What are those exponents? Well, those exponents represent how important is the effect of the voltage variation on the total power P, okay? P is P0 is the nominal active power that is consumed by your load. Then we have here this exponent that is extremely important, and this exponent say how is changing the active power when the voltage change. In a minute, I will tell you something. Depending of this exponent, we can create different types of loads, okay? For instance, what's happened if this exponent here is 0? Well, everything that you use a power of 0, that means this number is a constant and is equal to 1. That means in that case that there is not changes in the active power when the voltage change, because this model means that we are working at constant power, okay? Well, those equations over there that you can see for active and reactive power, they are included inside the model of the static load, the generic load that is included inside PowerFactory. If you look over there, I just open, there is a screenshot of the object that define the type of one load, okay? And you can see here, there are around 10 possible configurations, coefficients for A, B, and C, coefficients for the exponents, okay? And those coefficients are covered here for the active power, voltage dependence of the active power, and then voltage dependence for the reactive power, okay? If you want to read more about this, I highly suggest that you go to the PowerFactory technical reference in the case of the general load. And first, you will find a full section talking about the voltage dependence. The equations that I show over there in the slide came from the technical reference. And something that is extremely important for you is the selection. How important is the selection of those exponent values for different load behaviors, okay? As you can see over here, the exponent is related with this voltage ratio, okay? What's happening if we select 0? In this case, if we select 0,
Okay, this number here is 1, this number is 1, and this number is 1. As a consequence, they are not any voltage dependent at the loads. When we use those exponential coefficient at 0, the set value is 0, we are talking about a load that the power consumption has no dependence to the voltage. That is what we call constant power, okay? On the other hand, what's happened if we consider an exponent that is 2? Well, it's very simple. You can see here there is a number 2 at the exponent, and it's very simple to say that when the power, active power, depends on the square of the voltage ratio, that represents constant impedance. I believe you can see here that I present a screenshot of the configuration when you are using the exponent like number 2, and that represents the constant impedance. Constant current is a very specific model for the loads. We assume that there is a relationship that the active power increases linearly when the voltage is changing, okay? To be honest, typically we use the two important models, constant power and constant impedance. Constant current is typically used for very specific cases, but that is beyond the scope of this class, okay? What I will show you here is the numerical results. Now we are using the 5-bus bar system, the distribution feeder that we talk about. And here on the top, you can see the original values when we run the simulation, and it was not any voltage dependence, okay? If there is no voltage depender, the tail of this feeder, the voltage at bus bar number 5 is 0.82 per unit, okay? However, what's happened if we use constant impedance? Okay, we make the changes at the type of the loads, and now we run again the load flow. But when you run the load flow in this case, you must take in the load flow the option to consider the voltage dependence, okay? The first thing that you must know, you must recognize from the results, you can see that considering constant impedance makes changes on the power demand. I believe you can see, for instance, here in bus bar number 5, the original condition without voltage dependent was 2 megawatts power consumption. And that was for a load, for a voltage, a terminal voltage of 0.82. However, when we activate the option of considering the voltage dependence, and we say, okay, that load is equivalent to 1 impedance, what we can see is, first, the power consumption decreased from 2 megawatts to 1.4. But because the power demand here at the tail of the feeder decreased, the voltage in the radial system increased from 0.82 to 0.84, okay? What I'm trying to say is there is a very important impact when you are changing the model of your loads, okay? Considering the voltage dependence is something that makes changes on the result of your power flow, okay? Now, if you allow me to go back to one slide, probably the most typical question is, okay, we use constant power. For constant power, we use 0 for the exponential coefficient. If we want to simulate a constant current, we use 1. And if we want to simulate the loads as constant impedance, okay, we can use exponential coefficient that is 2. Now the question is, which model do we need to use?
Okay, that has been a very important topic, research topic for many years. In a lot of power utilities around the world, they conduct some studies, some research, and that research is looking into defining those coefficients. And another question is, okay, those coefficients, those exponential coefficients should be 0, 1, or 2. Well, the answer is not necessarily, okay? New research has identified that some loads has a behavior where the exponent coefficient is not necessarily an integer. I mean, it could be 2.50 or it could be a number with a decimal component, okay? Right now I will close the example about the voltage dependence on the loads. I hope that you understand that what you need to do is configure and make the proper settings at the load type. And also what you need to do is enable considering the voltage dependence of the load at the command load flow, okay? In a few minutes we will do it with that sample and you will see the process, okay? Finally, I would like to close this discussion doing something very simple but extremely interesting, okay? As I said before, in the past 15, 20 years, the power utility has changed a lot. More competitive markets, better technology, reducing the prices of power electronics and many other components. They open the door for smallest generators to compete in prices and efficiency with the big generators, okay? What I will do now is, okay, we have this very bad feeder, but at this moment, what I will do is, okay, let me put on service this synchronous machine, and this synchronous machine, it will work in terms of controlling or delivering some reactive power, okay? Because we are in a radial system, when we run the load flow, we realize, okay, in this generator, in this very specific generator, we are providing 0.8 megawatts, okay? However, because we set this synchronous machine in order to provide voltage support, you can see here on the configuration of this synchronous machine, this machine is working to provide voltage control. What is the good news? Well, this machine will deliver reactive power in order to keep constant the voltage at this bus bar. However, what is the cost, the technical cost of doing so? Okay, if you look the results of the power flow, you can see the voltage support, I mean keeping this voltage at 0.97, you will realize that you need a lot of reactive power. And to be honest, in this very specific case, the problem is that you are producing more reactive power than the active power that you are producing. And to be honest, in this case, you are overloading the synchronous machine, okay? This is very, very dangerous, because in this case we are not including the physical limits of active power and reactive power production, okay? All of you must be aware that synchronous machine, they have a limit about reactive power production, and the reactive power production is defined by several parameters. One of them is the capability of the rotor to receive a field current in order to produce reactive power, okay? As you can see over here, this machine is almost on fire because it's producing so much reactive power, okay? What I will do is, now let's be realistic, okay? If we open the model of this interesting synchronous machine, you realize
that this machine is opening so much the limits of reactive power. Okay, it's very, very insane that you will have a machine producing more, a synchronous machine producing more reactive power than active power. What we did here is try to reduce the power production, enabling some reactive power limits, and those reactive power limits are more realistic. In this case, you can see that we are moving from 0.7 to minus 0.7. That is the limits. We are including limits for the reactive power. However, defining the limits of reactive power is just one step, because when you are running the load flow, you must be able to enable the this reactive power regulation and considering the power limits. Okay, where is the place to do so? Okay, if you go to the command load flow, and when you open the window for configurations, you will realize that there is a region here that is on the top of the load options, and the third option is consider reactive power limits. Okay, now what we will do is sticking over there the option enabling PowerFactory to consider the realistic reactive power limits, and now we will run the simulation again. Okay, when we run the simulation again, what is the difference? Okay, when we activate the limits, you can see in this machine now it's producing 0.8 megawatts, and it's producing the biggest reactive power that they can do. In this case is 0.7, and of course it's reaching the limit of the reactive power, and as consequence the machine is not able to deliver more in order to keep constant the voltage. In that case, we are automatically PowerFactory is limiting the reactive power production, and is also as a consequence dropping the voltage. I mean, because there is no more reactive power to provide, it's impossible to keep constant the voltage, and now the voltage is 0.91. Okay, here I have a comparison between the two cases. As you can see here on the top, we have the previous case. You can see how the machine, the distribute generator is almost on fire. In this case, is overloaded. It's around 189%. The load is almost twice the load because it's producing 1.7 MVR. However, if we include the limits, the reactive limits of this machine, of course, in this case, the machine will be operating at the more realistic conditions. But those limits, you must be careful about those limits because they have effects on the performance of your power system. As a consequence here, the voltage is no longer supported by this DG. And as you can see, the voltage drop. Okay? I hope that you will be able to see how important is the reactive power contribution of DG units inside the distribution system. They can help, of course, if they have enough capability of producing reactive power, they can help. I mean, those new DG, they have possibilities of producing active power. We want active power because active power is mainly what we use inside homes. But keeping the lights on, keeping the distribution system working, we need more than just active power. We need also voltage support, and that can be done by the DG. Okay, this discussion here has been used in a classical synchronous machine. Why? Well, mainly because it's the most simple way to show the basic concepts. Okay, however, if you are using power electronics based technologies like PV system, wind power, or even batteries, the discussion is a bit more complex. Okay, if you want to hear more about discussion of power converter integrated
as DG inside distribution systems. There is a video coming very soon at my YouTube channel. Please feel free to go there and subscribe and wait until new release. Okay. Okay. Now we finished the explanation using the slides about using PowerFactory to assess the performance, steady-state performance, the power flow of a system, considering two important effects. One of them is the voltage depends at the loads, and the second is just a very basic and illustrative example, including a DG. Okay, please. Don't complain. This explanation about DG is just for very basic explanation and just for illustrative purposes. Okay. I know that some of you will say, okay, right now the technology that we have is not mainly based on synchronous machine, but I will use this as a way to introduce just basic concepts. Okay. If you want to know about integration of DG using power electronic converters interfaces, please subscribe to my YouTube channel, and then you will see a video coming soon about that topic. Okay. Okay, let's go to PowerFactory. In PowerFactory, I already have here this interesting distribution feeder. As you can see, is a single voltage distribution feeder. This is 13.8 kV. There are 1, 2, 3, 4 sections of distribution cables or distribution overhead lines. There are 5 bus bars. There are 4 different loads, and here we have the star that we will be talking about in a few minutes. Is the DG. Okay. The first thing that I would like to do here is let me put out the service this DG unit. Okay, this is the first step. Second, let me enable the result boxes. Okay, there is a button here at the top at the toolbar, and here now you can see the result boxes. Okay. What I will do now is let me start with a very basic load flow. In this case, I use the button, the icon at the toolbar, and I activate the command load flow. In this case, what I'm trying to see is, okay, there is only one option enabled, and is the calculation method, and we are selecting here the AC load flow. Okay, the classical AC load flow. In this case, we are using the classical AC load flow that is for positive sequence and is using a balanced network. Okay. Here we can run the load flow and we got the results. Okay. If you remember, at the head of the feeder, we have 1.05 per unit. That is the voltage that is coming from the distribution substation. And here we have at the very end, you must remember, it's a very poor distribution feeder. You can see 1.05 here, but then on bus bar number 2, the voltage drop around 7%. You go to around 0.97, here 0.91, 0.86, and finally at the tail, bus bar number 5, we have 0.82. Okay. Okay, that is the normal load flow. Now what we will do is, okay, let's do the following. I would like to show you first what is the effect of considering voltage dependence at the loads. Okay, a classical question is, okay, how do we define the voltage dependence at the loads? Okay, every single load here in this system, we have 5 loads.
you can see that there is, when you open the element, when you double click at the load, you will see that immediately below the name, there is a section to define the type that we are using for this load, okay? Something that you can identify is, in this case, I am using the same type of load. I am using, if you can see here at the loads, you can see that we are using the same type for all loads, okay? We are using the same type. And if you want to assess that, what we need to do is, let's edit and see the data of this load, okay? Of course, in this case, the type, you require a name, but also there is a section for the very specific of load flow, and at that tab, at the top of load flow, you have the full configuration of your voltage dependence at the loads, okay? There is a section for voltage dependence on active power. There is a section for voltage dependence at the reactive power, okay? By default here, you can see all the values are 0. If you remember from my explanation, we can go here to the technical reference and for models, or we can do something much better. PowerFactory is right now more helpful, and if you press F1, automatically it will open a PDF file, and this PDF file is pointing directly to the location of the technical reference for the general loads, okay? What I will do now is open here, and voila, we are right now inside a beautiful documentation, the documentation for the technical documentation for the general load, okay? As you can see here at my screen, there are a few sections. Let me go down. There are a few sections. One of the section here you can see is the voltage dependence. Is located in page number 5 in the case that you are using the version 2020 of PowerFactory. Let's go directly to this section. Let's go to the voltage dependence, and as you can see, PowerFactory include a model for voltage dependence that is basically using 3 polynomial terms. I already described them, and there are some exponential coefficient here that they are extremely important, okay? Why they are extremely important? Because in table 2.5 here at the technical reference, you can define different type of loads. For instance, constant power, if you select 0, or you can use constant current if you are using exponent coefficient 1, or if you prefer, we can go for constant impedance and selecting 2, okay? What I will do now is the following, okay? I close the technical reference, and what I will do is something simple. Let me close here, and remember, we run a basic load flow. Let me run the basic load flow. There is not voltage dependence at the loads. In this case, it's not enabled. And if we go to load number 2, you can see that the power that is defined here is 1 megawatt active power when the voltage is 1 per unit, okay? In this case, this is the nominal value, this is the rate value, but because we are considering no voltage dependence, PowerFactory automatically select constant power, and is selecting constant power, and you can see we put here 1 megawatt, and the voltage is below 1 per unit, but this load is still consuming 1 megawatts, okay? Okay, but now let's do the following. Let me modify the types of these loads. I will modify the type of these loads. and I will include a coefficient number 2 over there, okay? What I am doing now is including a exponent coefficient 2 for the voltage dependence, and there is a coefficient for CP that is 1 already defined. What I am doing now is all the loads will have a model, and the model that we are talking about is a model that includes a exponent coefficient 2 that is an impedance, okay? Impedance model. Now what I need to do is, let's say to PowerFactory, I will say to PowerFactory, okay, I want to consider the voltage dependence of loads, okay? We enable that option here at the very bottom of the command load flow. We click here and enable the voltage dependence, and then we will say execute. Okay? Something very interesting that you must realize. We were talking about this load number 2 because it was simple for me to show you the effect, okay? Because if we are using constant power, the power consumed by this load is 1.0 megawatts. But right now, because the voltage changed and we are considering the voltage dependence, you can see right now the consumption is 0.8 megawatts, okay? Now, if we go here, you can see that the original load power, the original power consumption is 1 megawatts. But because the voltage dependence is included, and in this case the power is changing with the square of the voltage ratio, now we have here 0.8, okay? What I will do now is again disable the voltage dependence, run the classical load flow without considering the dependency of the loads, and let me focus here at the tail. At the tail we have 0.82 is a very poor distribution feeder, and this load is 2 megawatts, and that is the nominal power of this load, okay? However, when we include the voltage dependence, what is the surprise? Wow. The surprise first is the actual power consumption here is 1.4 megawatts. Remember, if we are using constant power, the consumption is 2 megawatts, but because we are considering a model for impedance model for this load, when the voltage change, the active power depend of the square value of that voltage change. And that is very important, because if the voltage decrease, then if the voltage decrease, the active power consumption will decrease, okay? And that is positive for this distribution system, because if you remember, this was a very poor distribution system, and in this case, the voltage was 0.84, okay? What I want is that you understand there is something called voltage dependence. This click over here enable the PowerFactory to consider the voltage dependence, but you must configure the voltage dependence at your model, and that is located inside the type object of your loads, okay? In this case, I select the same type for all the loads, okay? One question that could rise extremely fast is, okay, is that true? All the loads have the same model. Well, realistically speaking, is not necessarily true, okay? Realistically speaking, some loads are different to another loads, even in the same geographical location. However, in a residential area, we can say that all the loads connected in that area have a very specific type, and we can assume that all of them are behaving in the same way, the same voltage dependence, okay? Okay,
Something that I want to show you also right now. Let me go back to PowerFactory. Let me deactivate the load, okay? And now what I will do is the following, okay? What I want to show you, we came back to the original conditions of the distribution feeder, a very poor voltage 0.82, okay? Now what I will do is, first I would like to start with a short discussion about something probably it's not relevant, but people must care about small details, okay? Small details are very interesting, okay? At the very beginning of this session, I put out the service this generator. Some of you must remember previous of my videos, previous videos of mine, that instead of doing this, I open the circuit breaker that is connected to the generator. And probably you are wondering, okay, what is the difference is if I open the circuit breaker, or instead of opening the circuit breaker, I put out the service. And I believe you can see the real difference. I mean, from the numerical point of view, the solution of your power flow, there is not different. There is no different. Why not? Because you are disconnecting or you are switching off the generator. They are not different. The power contribution, active and reactive power of that DG unit is 0. But I don't know if you realize that if we put out the service, the generator, and we run the load flow, there is no numerical results here. There is not numerical results at the generator. But instead, if I use just opening the circuit breaker, you can see that now you got some results. Opening the circuit breaker in PowerFactory is different to an outage or putting out the service. When you say out the service, that means that the component, the device, is removed from the calculations. But when you open a circuit breaker inside PowerFactory, PowerFactory keep this device, and this device is included on calculations. And you can see over there, it's saying 0. All the results are 0 for this machine. However, it's taking in account for the numerical solution, okay? Probably for load flow is nothing really important for you, but in other of my videos regarding power system dynamics, you will see that this has very important effect on your simulations, okay? Well, at the moment, what I will do is I will close the breaker, because now what I will do is I will switch on my DG unit. In this DG unit is a classical synchronous machine. I know probably some of you will say right now we are using power converter based technologies like PV system or wind power, but in this case I just want to show you just an introduction, just a small taste about DG, okay? In this case, I will go to load flow, and I will go to load flow to show you what is the configuration of this synchronous machine. In this synchronous machine, we have an active power injection of 0.8 megawatts. And I am doing something that is not quite typical, but I am using the configuration of local voltage controller in order to keep the voltage constant. And I define the voltage that I would like to keep to 0.971, okay? Okay. And right now, what I will do is we close the breaker. Now this DG is connected, and let's say to PowerFactory, run a power flow, okay? What is the good news and the bad news? Okay, right now we have a DG that is installed in bus bar number 4, is producing 0.8 megawatts. The voltage at bus bar number 4 increased. Congratulations, that is extremely good. However, there is a big problem over there.
This machine is working in order to keep constant the voltage at the terminal, 0.97, okay? However, I don't know if you realize that in order to keep the voltage at that level, this machine is almost on fire. Because if you can see the power, reactive power production is 1.7, okay? What is the reason for that? Well, right now we are using a synchronous machine, but this is not a realistic synchronous machine. In a real synchronous machine, there are limits. There are limits for the reactive power that you can produce, okay? I will not go in full details, but you must remember from your classes of electrical machines that synchronous machine has operating limits, and they are related with some physical constraints. For reactive power production, one of those physical constraints is related with the maximum current that you can install, you can put or you can fit inside the rotor winding, okay? What I will do now is, in this case, the machine is on fire. We have an overloaded machine. What I will go now is to load flow, the tab for load flow. I will keep the controller as constant V in order to try to support the voltage, but I will go to the reactive power limits, and I will say, okay, let's do the following. Let's use this. Let's consider those limits, okay? What I will do is I will reduce a bit more the limits, okay? In order to reduce the reactive power production, okay? I believe you can see that when I am doing that, PowerFactory is modifying the capability curve, the PQ curve of the machine, okay? Of the machine. Now what I will do is, now let's consider the limits of reactive power limits at the synchronous machine. Now I run the power flow. Wow, voila. Well, right now we have here a relative load synchronous machine, around 82%, is producing 0.8 megawatts, 0.2. However, the voltage drop. Now the voltage is 0.88 because the synchronous machine is reaching the limit. In this case, the limit is 0.2 MVR, and as a consequence, this machine is not able to keep the voltage constant. What we can do here is, okay, let me open a bit more the limits, the reactive power limits of this machine. Let me double click. Let me go to load flow tab. Now let's say that the reactive power could be 0.3, 0.3, and 0.2, 0.3 and 0.3, okay? I am opening a bit more the reactive power production. I will run again a load flow considering the reactive power limits. Now the machine is producing 0.8. The machine is reaching the reactive power limits, and the voltage is improved to 0.89, okay? What I would like that you understand is, depending of the operating mode, if you can provide reactive power or not, you can improve the distribution network performance. You can use, for instance, to improve the voltage profile, but also, if you wish, you can use to reducing the power losses, okay? Let me do something very simple here, okay? I will double click at the synchronous machine, and now I will change the operational mode, and I will say constant Q. But now I will say, like in a typical or a very typical PV system, this synchronous machine is only producing active power, okay? If this machine is producing only active power, there is no possibility to control the voltage, okay? Then what I will do is run a load flow, okay? And here now this machine is producing only active power, and the active power is 0.8, okay? What I will do now is, this machine is producing 0 reactive power. Let me reduce the active power to 0.1, okay? 0.1.
And what I want to show you is a very small effect related with the power losses, okay? What I will do now is I will enable here and text boxes, summary box, okay? What is the total active power losses, okay? Let me find here, total active power losses, 0.09 megawatts, okay? 0.09 megawatts. Now, let me increase the power production here at this unit. I will increase to 1 megawatt, and I will run again the voltage without considering the limits, but this machine will be running right now zero reactive power, 1 megawatt, okay? Now, I believe you can see something quite interesting. Now you can see that the total active power losses move from 0.09 megawatts to 0.07 megawatts. What I'm trying to say is using local generation installed close to the demand, or what we call DG, is especially positive for distribution system if we have the appropriate control and the appropriate operating mode for those machines, okay? Well, I think that is all for today. Thank you very much for attending to this class, and it was a pleasure having you, okay? See you in the next chapter. Thank you. Finally, I would like to close this class with a summary. In this case, I would like to say that we present a very generic and brief and short introduction about power flow problem in electrical power system. I try to do a basic explanation about basic concepts inside the power flow calculation, the admittance matrix, the power balance equation, then what is the formulation for the the power flow problem, then what are the numerical methods used for the solution, and comparison between the different solution techniques. As I say in that section, Newton-Raphson is probably the most used method for solving the power flow problem, and it's that the power that is the method used inside DIgSILENT PowerFactory, okay? I present a couple examples, one of them presenting the common difference, and I present a small system, a radial distribution system, in order to introduce the concept of voltage dependence of the loads and the use of DG to improve voltage profiles, okay? Well, thank you very much for attending to this class. Thank you very much for watching the video. Again, I would like to remind you, please subscribe to the YouTube channel, and you will get information about the updates of when I upload a new video, okay? Thank you very much for your time and for attending to this class. Thank you.